fields such as physics, chemistry, engineering, biology, etc. And it makes a breakthrough that will change the direction of nanotechnology advances in large range of applications. A variety of organic and inorganic nanomaterials with dimensions below several hundred nanometers are recently emerging as promising tools for cancer therapeutic and diagnostic applications due to their unique characteristics of passive tumor targeting. I am very pleased to welcome Dr. Gopinadhan Nair, the speaker of the last session of our webinar series today. He took his master's degree from the University of Madras and pursued his MPhil from Bharathidasan University in 2007. Dr. Gopakumar, who will be giving us a presentation on the topic nanomaterials and its application in cancer therapy, holds PhD on the topic drugs bound to silver nanoparticles, its biological activities and potential applications in radioprotection and cancer therapy under the guidance of Dr. C.K. Nair, scientist, BARC Radiation Biology Division, and he took his PhD from Amala Cancer Research Center in 2015. After his doctoral degree, he was working as a senior scientist in Metabolic Disorders Research Center for a year. He was the deputy manager of the R&D division of Plant Lipids Private Limited, and later he shifted his steps to AK Flavors as a scientist. He moved to Milwaukee State of Wisconsin, US for his postdoctoral research in 2017, and currently he is continuing his postdoctoral research in the University of Oklahoma Health Sciences Center, US. He has been invited by several prestigious institutions to share his ideas. And coming to the publications, he has published 14 papers in international journals of high impact factor and 9 research papers in national journals. Recently, he has added a paper in cancer research too. He is the reviewer of many journals and has contributed chapters to ethnomedical plans to fight against the neoplastic diseases. And he has attended and presented research articles in many national and international conferences. With these words, I invite our resource person for presentation. I request you all to give your full attention to Dr. Gopakumar. Dr. Gopakumar, please.
Thank you, Priya. And it was a warm welcoming. And first of all, I express my sincere thanks to Dr. Biju Thomas, Principal, Baselius College, Dr. Suma Bino Thomas, Head of the Department, Dr. Jinda Thomas, Coordinator, and all the organizing committee members. And a special thanks to Dr. Priya for inviting me to deliver this talk this day. Thank you very much. So I'm going to start my talk. Good morning, all. Today I'm going to speak on the application of nanoparticles in cancer therapy and diagnosis. As everybody knows, cancer is one of the most common diseases in the developed world, and throughout the world, cancer mortality and incidence are increasing, and 1 in 4 deaths are due to cancer all over the world. Common cancer types by National Institute of Health are bladder cancer, breast cancer, colon and rectal cancer, endometrial cancers, kidney cancer, and etc. The most common type of cancer on the list is breast cancer, with 279,000 new cases expected in the United States in 2020. The next most common cancers are lung cancer and prostate cancer. And we all know the early diagnosis of cancer is very critical. Cancer diagnosis and imaging play a major role in the prognosis, staging, and treatment planning, and the evolution of treatment response. There are 2 types, basically. They are non-invasive, invasive imaging techniques and the invasive imaging technique. The non-invasive imaging techniques are, as we know, magnetic resonance, that MRI, CT scanning, and radiography, nuclear imaging, positron emission, computed tomography, that is a PET scan, and ultrasound systems. But each of these techniques, they have their own limitations, and their properties are uniquely suited to some diagnostic scenarios and unsuitable for the others. And invasive diagnostic technique is the biopsy, that taking the sample from the tumor tissue or whatever the tissue, and then checking whether it is tumor or not. And it is the biopsy, if there is a high uptake of FDG, that is fluoro deoxyglucose, is in clinical practice where a lesion will be told a cancer or not. And the cancer therapy, there are, as we know, there are three main types: the pharmaceutical treatment, that is the chemotherapy, hormone therapy, and immunotherapy; radiation treatments, as we know, it is radiotherapy; and the physical intervention, that is resection, surgical removal of the tumor. So in all these cases, there are a lot of problems, that is damage to normal tissues, or sometimes incomplete eradication of the cancer is the result. Nano targeting is a way to aim the therapies more directly towards the tumor cells. As we know, chemotherapy is the most common cancer therapy. It has got very narrow therapeutic index in many cases, because when it is used singly, it will not give the proper drug outcome. So to overcome the drug resistance or mechanism, multiple chemotherapeutic combination is used. After all, it will affect the normal cells also. It is not a targeted therapy. Some drugs can damage even in the younger people, spermatogenesis or oogenesis, and causing infertility, amenorrhea, early menopause, or impotence. And most of the chemotherapeutics cannot be used during the first trimester of pregnancy because of their teratogenic effect. And many chemotherapeutic drugs, they are chemicals, as we know, and they have mutagenic effect, leading to secondary neoplasms in later stage. Some anti-cancer drugs are cycle specific, that is the cell cycle, and such as the synthesis phase alone, and they can be, so they have limited, they will mostly target these fast proliferating cells. And unfortunately, there are, like our hair cells and the gastrointestinal system, blood cells, they are fast proliferating cells. So they will have side effects, a lot of side effects. And the age, patient-related factors like age, health, immunity, all matters when chemotherapeutic is administered. And coming to the radiation therapy, they have got targeted effects and non-targeted effects, that is adverse effects, that damage the DNA, that damage lipids and proteins. And non-targeted effects may generate the free radical generation, and they cause bystander phenomenon, that is the release of growth factors, cytokines, interleukins, and ultimately damage the neighboring cells, that is extracellular membranes of the normal cells, and intracellular damage of the cells, and they cause the cell cycle arrest, genotoxicity, DNA repair, and apoptosis, ultimately causing the cell death of the normal cells also. And nanotechnology, why nanotechnology is very much important is because nanotechnology, it is designed, actually nanotechnology is the manipulation of matter on atomic and molecular scale. It refers to the interaction of cellular and molecular components and engineered materials at the most elemental level of biology. And this, my presentation is mainly focused on the utilization of nanotechnology in the treatment of cancer. So it is the size actually matters. The nanoscale of that is, it is 10 to the power of -9 is called nano. Nanoscale is the nano drugs or therapeutic molecules, which will be in the range of 1 to 100 nanometers. And they have got a lot of novel applications, like imaging techniques, and their optical features make them more useful in the imaging with the our conventional imaging techniques like MRI or CT scan, etc. And nanotechnology bridges the border between the physics, chemistry, and medical research. And how small are nano devices? As I have told, it ranges between 1 to 100 nanometers. When we compare the normal, our eukaryotic cell, it is about 10,000 to 20,000 nanometers. And here comes the nanoparticles and the nano carriers. They are in between the range of our antibodies and the virus particles. Viruses are above 10 to the power of 2 nanometers range. And so what, and that this size and size specific nature of these nanoparticles enables them to enter into the cell and deliver the drug molecules. And why we have to depend on nanotechnology? Why nanotechnology? Difficulties in early detection and treatment of the cancer, and there is no immunization. Actually, now in the case of cervical cancers, that is viral cancers, immunization is there, but other cancers, no immunization. And ineffectiveness and side effects of relevant therapies like chemotherapy and radiotherapy or even surgeries, uh, nanotechnology will be a suitable option. Higher surface area and the ability to undergo faster redox reactions enable them to, have more drug particles bound to them and deliver it to the target. So these nanoparticle delivery is targeted and enhance scavenging of harmful free radicals. Also, they have a free radical scavenging activity. And theranostics is a new area, that is the therapeutic agent is bound to the nanoparticle, means like engulfed in the nanoparticles, and the targeting agent, that is the antibody which targets the antigen on the tumor surface proteins, and that will target the drug complex to the directly to the tumor site and deliver the drugs into the tumor, and it can be utilized for the um, imaging and detection of the cancer, as well as for the treatment of the cancer. That is therapy along with diagnostics is called theranostics. And nanoparticles can be exploited to target biomarkers or antigens that are highly specific to cancer. That is, EGFR is one of the main, it has been already been told that discovered late 80s that EGFR is present in all cancers, and they are utilized for the detection of cancer cells with nanoparticles. They are in nanoscale and can easily invade in the eukaryotic cells, as I have told earlier, and they can detect the nanocarriers or nanodetection molecules can detect diseases in cellular level. And how nanoparticles are synthesized. Actually, there are a top-down and a bottom-up mechanism, and also a safer mechanism called the green or the biological synthesis of nanoparticles. And the top down, they are mostly chemical synthesis of nanoparticles, and bottom up also it is chemical synthesis, and but biological synthesis is a bottom up synthesis, and it is a safe and green synthesis of nanoparticles with no toxicity at all. So in the case of top down processes, a bulk metal or non-metal can be reduced in their size to fine particles using a reducing agent, and stabilization of that fine particles leads to the usable nanoparticles. Here I have shown the preparation of gold nanoparticles, silver nanoparticles, and this is the bottom up mechanism where the ions, actually silver ions are reduced using a reducing agent and a capping agent which stabilizes the particle. That can be non-ionic emulsifying agents or polymers that coat the nanoparticles, and then stabilizes the nanoparticle to form the real nano carriers. There are various kinds of nanoparticles used in therapeutics, as well as for the imaging techniques, detection of the diseases. They are lipid-based nanocarriers. Phospholipids are used, and solid lipid nanoparticles. They are the under certain heat conditions, they will be solid, and when heat is, or we can use the ultraviolet or infrared, near infrared, and they will melt the solid lipid nanoparticles. And this is highly used in, they are safer and used in many of the drug complex development. And polymer-based nanocarriers, they are polymeric micellar or the albumin-bound technology. Nanoparticle is widely used in the case of paclitaxel drug delivery, and the polymeric nanoparticles, then the inorganic nanoparticles like metal and the non-metals. They are also widely used in detection like MRI diagnosis and all. And the viral nanoparticles, they basically make use of the plant viruses and baculoviruses, and then drug conjugates with the nanoparticles where the drug is conjugated, that is dendrimers and all, where the drug is coated like antibodies is coated. It can be used for even targeting the tumor cells for detection of tumor. And what is the advantage of molecular imaging and therapy using nanoparticles is that it is specific cancer diagnosis. The nanoparticle detection molecule can be directly targeted to the cancer cells. And if the cancer cell is diagnosed, a targeted medication can be given targeting to specific to the, when the drug is given, the nanoparticles and the medication directly target to the cancer cell, and they only kill the cancer cells and leaving the normal cells healthy. And cancer detection, current imaging methods helps in diagnosis when tumor grows to a detectable size. And by that time, metastasis would have happened. And for even after, they can only find out the size with the size of the tumor. So we don't know whether it will be benign or malignant. So biopsy is needed, IHC is needed, that is immunohistochemistry for various markers for cancer should be done. But nano-targeted detection imaging helps to detect precancerous cells by tagging antibodies that identify cancer-specific receptors that produce high contrast signaling with MRI and CT. So nanoparticles can, that is for detection, it can be utilized with the conventional MRI or CT methods. And nanotechnology will enable the visualization of molecular markers that identify stages and types of cancer. More cancer-specific biomarkers in single analysis. Quantum dots, I will be coming to this later. And quantum dots, they are nanocrystals used for the detection of cancer as well as for the treatment of the cancer. And these are some of the nano devices in cancer detection. They are quantum dots, magnetic nanoparticles, and gold, metal or non-metal nanoparticles, and polymer dots. And their surface area is higher compared to any other drugs or anything. So they carry, when the drugs are conjugated with the bound to nanoparticles, it can load more drugs and deliver to the site without damaging the normal cells. So nanoparticles, they can be attached with targeting peptides, aptamers, fluorescent probes for detection, antibodies specific to the antigens on cancer surface, and then PEG linker for the antibody linking or antigen linking, and small molecules. So they can target proteins, DNA or RNA, and the circulating tumor cells, and exosomes. It is a new area. Exosomes are the extracellular vesicles. They are very much involved in the transfer of proteins from cells inside the cells to outside extracellular matrix, and it helps in the cell-to-cell talk. So tumor cells shed exosomes with proteins that talk with other cells, and it is now very much used in the cancer detection as well as for the therapy. So these are the some of the mechanisms: in vivo tumor imaging and passive targeting and active targeting. I'll come to them later. And protein circulate detection of biomarkers on the cancer cells, like protein level, circulating tumor DNA, microRNA, and extracellular vesicles, and detection of cancer cells based on the cell surface protein circulating tumor cells and based on their mRNA. Nanotechnology aims the therapies directly and selectively to the tumor. That makes it very promising in the field of detection and cancer therapy. The different types of nanotherapy uses nanocarriers. They are low degradation. They are low degradation. So when they are entered into the body, they will slowly. They will not degrade fast. So they will maintain the drug for longer period and makes them enhance the absorption of the drug and controlled release of the drugs, makes them more effective. And passive targeting, it is the EPR, that is enhanced permeability and retention of the drug, that makes some tumor cells, they have a leaky vasculature and they have a like lymph vessel leakage. And then so what happens, this passive targeting can be exploited. This nanoparticles can directly invade into the blood vessels, and they will be deposited directly into these tumor cells because of their leaky nature. And then there we can detect the this can be utilized for drug targeting as well as for the detection of the tumor cells. And passive targeting is also used with active targeting. Active targeting, they nanoparticles are bound with antibodies or the antigens that target specifically to the tumor cells, and then they are encapsulated. They will encapsulate the drug molecules, and when they target and attach to the tumor cells specifically, they deliver the drugs into the cancer cells. And the destruction from within, actually nanoshells, they can excited with near infrared, and this is called heat killing, because normal cells will be damaged at temperature above 46 degrees Celsius, while a cancer cell can sustain under up to 42 degrees Celsius. So the nanoparticles, the nanoshells, they are spherical nanoparticles. They coated with drugs, and they can be targeted into the tumor cells, and giving a near infrared light, they will be heated up, and then causing the tumor cells to go into death. That is specific targeting of tumor cell killing. And nanopores, nanopores are like they are holes where a single strand DNA can go, means like move into it, and each bases or the tags are like sequenced very fast, and error specific to the cancer DNA can be easily detected using nanopores. And the nanotubes, they are tubular cancer, means like carbon tubes. They also can locate the mutations in the DNA, and they can predict the exact location of the mutation, and disease can be predicted. And the quantum dots are, as I've told, they are nanocrystals. They will be labeled with fluorescent tags, and when a UV light is excited, they can be, they specifically go to these quantum dots. They specifically goes to the nano means like cancer cells, and then with their labels, if it is a cancer cell or a specific antigen is produced, they on the UV light irradiation, they will illuminate, and then cancer can be detected. And the dendrimers, they are encapsulated they have an dendrimers, they carry the nanoparticular and drugs, and the dendrimers are macromolecules, but they carry the nanoparticles and encapsulated with a hydrophobic coat. And this can be with the pH difference, or with the heat difference. The encapsulated hydrophobic coat will be melted, and the nanoparticles can be directly delivered to the site. So they are highly used for drug delivery system, and even many of the dendrimers drugs are used in cancer therapy, and they are approved. So, and we all know liposomal nanoparticles are very safe and very easily usable to deliver drugs, as well as for the detection of diseases. They use phospholipids and surface ligands they target the surface ligands of the cancer cells, and they can detect the cancer cells. And I have told this is one of the paper by Young et al. In 2010, came in census. So they use the EGFR, that is epidermal growth factor receptor, is widely popular biomarker used in cancer targeting. They use the Raman spectroscopic Raman reporter conjugated with SCFV, that is a fragment chain, and antibody for in vitro and in vivo tumor targeting. And these are, you can check the clinical trials which are going on and recruited, or in the NIH website, that is US National Library of Medicine clinical trials, which are going on and approved and recruiting the volunteers for their trials. And these are new approvals, that drugs which are approved. This is a liposomal formulation of cytarabine and daunorubicin. It is used for acute myeloid leukemia. It is approved by FDA in 2017 and European Medical Association in 2018. And it is used for various leukemias. And NBTXR, it is a hafnium oxide inorganic nanoparticle stimulated with external radiation to enhance the tumor. And these are other nanoparticle drug complexes used for the treatment of various cancers. And this is the paper that is nanoparticles in the clinic. An update by Aaron et al. Came in the review Bioengineering and Translation Medicines. You can go and look into that for updates of clinical trials and approved drugs in cancer, nano drugs in cancer therapy. So coming to, and now I am going to like give a presentation on the works which I have done. It is I have used silver nanoparticles for the drug delivery. So silver has got a lot of medicinal uses going back from centuries. It has got germicidal property and disinfectant properties, and it is an excellent free radical scavenging agent, and it has got anti-inflammatory and anti-tumor activities. My topic is silver nanoparticle complexing of hypoxic cell sensitizer, senosol, that is AK2123, which is a clinically proved drug and like completed phase 3 clinical trials. And it is a combination with chemotherapeutic doxorubicin and for enhanced anti-tumor efficacy. Senosol, it is a nitrotriazole hypoxic cell sensitizer. It has been widely used in combination with thermotherapy, chemotherapy, and radiotherapy of cancers. And clinically, tumor hypoxia reduces the effectiveness of radiation therapy as well as chemotherapy. Once the peripheral tumor cells are dead and shed killed by the radiation therapy, the core tumor, which was not getting nutrition previously, and where the oxygen is less reduced, and because of that, the tumor radiation therapy will not be effective. later, once the radiation therapy is done, all the patient will be sent home, and after a few years or months, the core tumor started, active, and makes the secondary tumors. So, senesol, which was reported to induce apoptosis in murine fibrosarcoma cells and enhances the level of caspase-3 enzyme and internucleosomal fragmentation, has been used in my study. And it's combined with a very well-known chemotherapeutic agent, doxorubicin. It is also known as anthracycline. It's an antibiotic, anthracycline antibiotic produced by the fungus Streptomyces pcts. Most effective, it is said to be the most effective chemotherapeutic agents for hematological and solid malignancies. Doxorubicin damages DNA by intercalation or by generation of free radicals. Anthracyclines are well known for their cardiotoxicity, and cardiotoxicity is a serious risk in doxorubicin therapies. Excuse me. And this is how the preparation of silver nanoparticle complex of senesol and doxorubicin has been carried out. The SN nanoparticles, which was obtained from Dr. Khanna, CMET, Pune, and we have used a non-ionic emulsifying agent, POES, that is polyoxyethylene stearate, and we made a colloidal suspension of silver nanoparticle POES and added 1% of SN and 5% of polyoxyethylene for this colloidal suspension, and then 1% of AK, that is senesol, and 0.1% of doxorubicin. And they were sonicated, ultrasonicated, and we took like SN dox, SN AK, SN AK doxo combinations for our studies. First, we have checked the cytotoxic effect of these drugs and their complexes on DLA solid tumors cells, that is Dalton's lymphoma ascites cells, which is a murine tumor cell. And we have found that the combination drug has got like high potency in killing the tumor cells. And we have done the induction of check the induction of DNA strand breaks using the Comet assay, and we checked the percentage DNA in the tail, that is the damage caused to the DNA. The percentage of damage caused to the DNA and olive tail movement, it is a product of the tail length and the percentage of DNA in the tail. And it was found that the complex could induce DNA strand breaks in the DLA cells effectively than the drugs alone or the nanoparticle alone. And induction of apoptosis was also studied, and it was shown that the drug complex synergetically induce apoptosis in the tumor cells. This is a representation of the apoptotic cells stained with normal cells and the apoptotic cells stained with acridine orange and ethidium double staining. And the green perfect round cells are viable cells, and necrotic cells are red cells. This orange is red cells, and this is a early apoptotic cells with cellular blubbing and DNA fragmentation. And this is a late apoptotic cell having orange to red nuclei with condensed fragmented chromatin. And we have also studied an in vivo assay, that is tumor regression in the DLA induced solid tumor bearing mice. And we have found that the tumor volume was highly reduced in the mice with SNAK dogs complex. This is the pictorial representation. This is the control animal, and this is the treated animal. It has, like, most of the tumor has gone. So the summary of the study is that the SNAK dogs enhanced the cytotoxic property of cynosol and doxorubicin and showed chemosensitizing action, which resulted in improved anti-cancer effect, induced DNA damage and apoptosis in tumor cells more effectively than the individual drugs components, and rendered significant reduction of tumor volume in DLA solid tumor bearing mice. And my next study was like radio protection by phytophenol sesamol and its silver nanoparticle complex and their application in tumor therapy. So we have, the study design was like anti-inflammatory activity. So animals were used and acute models using the carrageenan and dextran pyoedema, and chronic model using the formalin-induced pyoedema has been studied. And the radioprotecting ability of the complex by experiments, like doing experiments, checking the membrane lipid peroxidation, endogenous antioxidant status, hematological profile, gastrointestinal damage, genotoxicity, body weight alterations, and mortality. Adjuvant role in tumor therapy also was studied in radiotherapy, tumor growth delay, in chemotherapy, doxorubicin, cisplatin induced toxicities. Sesamol, it is a 5-hydroxy-1,3-benzodioxole or 3,4-methylene dioxyphenol. It is obtained from sesame seeds, and it's a derivative of phenol. It is off-white and crystalline solid, and it has been showed high antioxidant activity and radioprotecting ability. And we have used silver nanoparticles obtained from Dr. Khanna. And here we have used a non-ionic surfactant emulsifying agent, that is pluronic F127. And using ultrasonication, made the pluronic silver nanoparticle colloid suspension, and drug was added at 1% of SM and 0.1% SN nanoparticles to obtain the sesamol silver nanoparticle complex. And we have done a TEM imaging of our drug complex and found that the drug was ranging like below 200 nanometer size. And this is the original electron microscope image of the silver nanoparticles. And this is after preparation of the drug complex. It is done at a sophisticated test and instrumentation center, STIC, QSAT, Kerala. And this is the X-ray diffraction pattern of SN-SM. And on synthesis of the drug complex, it has become an amorphic nature, and the peaks are like soft than the peaks from the original nanoparticles. It has been done in the Royal Institute of Technology, Sweden. So we have studied the anti-inflammatory activity of SNSM, and it was found that even in the acute models and the chronic models, the complexes complex at 80 mg equivalent SM kilogram body weight of the animal showed very good reduction in the inflammation in the animals. And we have checked the various antioxidant lipid peroxidation status in the animals, and it was found that the lipid peroxidation was highly reduced after drug treatment on the gamma irradiated animals, whole body gamma irradiated animals. We have used different doses of radiation from 2 to 8 gray, and it was found that the drug could synergetically reduce the lipid peroxidative action of radiation in various tissues. And it was also found that the endogenous antioxidant status in the various organs of the irradiated mice was restored with the administration of the drug. This is the very in the liver tissue, and this is in the brain tissue. It is restored to normal ranges. And blood GSH content and the bone marrow cellularity in radiation exposed mice showed significant protection in the antioxidant status of irradiated mice, and the like bone marrow cellularity was restored in the SNSM treated mice. And radiation causes gastrointestinal injury, and we have found that the irradiated 6th grade irradiated mice has got damaged intestinal crypt epithelial cells and cause necrosis and blunting of the villi. That this is a normal one and this is the irradiated one, and the drug treatment completely restored the protected the animal from gastrointestinal damage. And spleen colony formation in radiation exposed mice, it's a um, factor of like restoration of the pluripotent stem cells in the spleen, and it was found that number of spleen colonies were high in the SNSM treated irradiated mice spleen, and the spleen weight was like also normal in the SNSM treated mice. So this is the normal spleen and the endogenous spleen colonies formation after irradiation when the animals were treated with the drug complex. In other cases, splenomegaly, enlargement of the spleen will be resulting and lead to complications. And we have also studied a radiation-induced mortality. A lethal dose of 10 gray radiation was given to animals, and they were administered with the drug after irradiation and one time before the irradiation. And it was found that the animal survival rate was highly enhanced with the administration of the drug complex. It was like 30% survival advantage was seen in the drug complex treated 10 gray irradiated animals. And we have also checked a in vivo radiation induced genotoxicity in the blood leukocytes and bone marrow cells, and it was found that DNA damage was excuse me, highly reduced in the drug treated animals, SNSM treated animals. It was like a significant reduction in the DNA damage. The repair rate was, it shows the drug could repair the damage after gamma irradiation. So this is a representation of the single cell gel electrophoresis comet assay, and this is the damaged cells after irradiation, and that DNA damage is repaired in the case of SNSM treated cells. So this is a unit of DNA we have studied to quantify the efficiency of cellular DNA repair. A relation based on the comet parameters named cellular DNA repair index was arrived, and it was found that when the CRI index is high, there is a fast repair rate, and when the CRI is low, there is a low repair rate. So in the foreground irradiated non-treated animals, the DNA repair was less and damage was more, and in the case of SNSM treated 4K irradiated animals, the repair rate was very fast, and there is a high rate of normal restoration of the DNA. Excuse me. So another study we have done is the radiation-induced genotoxicity, is a micronuclei assay. Micronuclei are formed in the reticulocytes, that is the immature red blood cells, when when it is irradiated and causing the chromosomal damage, breakage. So that is studied, and it was found that the control animals with 2 gray radiation after 48 hours showed like 7.6 numbers of micronuclei in their reticulocytes. And in the case of the drug treated, the micronuclei was highly reduced. That shows the drug treatment protects the normal cells. And radiation-induced chromosomal damages, that is, this is a normal chromosomal spread. And in the case of irradiation or chromosomal damage, irradiation that causes, radiation causes dicentrate or pulverized chromosomes and breakage, acentric fragments, and triradial or ring formation, and different types of chromosomal damages. And we have studied in the radiation-induced genotoxicity with chromosomal aberrations, and it was found that the chromosomal aberrations were highly reduced in the case of SNSM treated mice, bone marrow cells. And the very severe damages were also highly reduced in the SNSM treated groups. And we have also studied a tumor reduction in the DLA solid tumor bearing mice, and it was found that the nanoparticle drug complex has showed a very significant reduction in the tumor volume in treated animals. And we have also checked the nanoparticle drug complex in the cancer cells, whether it induces apoptosis, and it was found that SNSM with the radiation showed a large number of apoptotic cells with DNA damage and the membrane damages. And it was the apoptotic index was like 80%, and in 4 hours with the drug treated DLA cells. So it shows the killing efficiency of the nanoparticle drug complex compared to either the sesamol alone or with the means only 4-gray irradiation. So, and in combination with SNSM, gamma radiation, there was an induction of DNA strand breaks in tumor cells, and which was studied using the COMET assay. And it was found that in the tumor cells, the DNA damage was, the breakage was more, and the damage repair rate was very less. This is a ladder pattern of the DNA from the tumor cells, DLA tumor cells, after treating with the SNSM, the gel electrophoresis from the samples from animals, the solid tumor samples from the animals. So it was found that SNSM has showed DNA damage, showing the data like this is a normal control with no damage, intact DNA. And we are aware of the cardiotoxicity of doxorubicin. And so I have checked the antioxidant status of heart and tumor to establish and say that the drug complex has got preferential protection of the normal cells, and it protects the animals from the doxorubicin toxicity. So in the tumor, it was found that the lipid peroxidation was high, and the endogenous antioxidant status were lowered with the treatment, while the drug could maintain the endogenous antioxidant status and control the MDA, that is lipid peroxidation, malondialdehyde formation in the tissues. So it is clear that there is a preferential protection of the normal cells and a killing of the active killing of the tumor cells with the drug complex. And SGOT, SGPT, as we know, it is also a marker for the cardiotoxicity, and CKMB, it is a creatine kinase specific. It is a complex of like two enzymes, isoenzymes, that is CKM and CKB, and it is highly reduced with the drug treatment in the cardiac tissue. And LDH is also a marker for the biomarker for cardiotoxicity, myocardial infarction, and it is also highly reduced in the drug treated groups. So this is a histopathology section of heart tissue, and it was found that there was a damage in the untreated group, myocardial degeneration, loss of myofibrils, and focal cytoplasmic vacuolization, and it was restored with the treatment of SNSM. And another is the cisplatin-induced nephrotoxicity, and it was found that the drug complex of SM could give substantial protection to the normal kidney and the kidney cells, and destruction to the tumor cells from the values of MDA. It is high in the tumor cells and restored, reduced in the maintained in the normal kidney cells. And the endogenous antioxidants were also high in the kidney cells and very much reduced in the tumor cells. So urea and creatine, as everybody knows, is a biomarker for the nephrotoxicity, and the creatine levels and urea levels were highly maintained in the drug treated group, the drug complex treated groups. And the histopathology also showed damaged nephro cells, kidney cells, and restored with the treatment of SNSM. And the summary is SNSM showed significant anti-inflammatory activity in both acute and chronic inflammatory models, inhibited the radiation-induced peroxidation of membrane lipids, helped to maintain endogenous antioxidant status, and bestowed protective effects on hematological and gastrointestinal systems after radiation, and prevented body weight alterations and increased survival rates in radiation-exposed animals, showed protection against radiation and induced genotoxicity in normal cells, and damage to the cancer cells, and exhibited synergetic action with radiation in delaying tumor growth, suggesting its feasibility as adjuvant in radiotherapy of cancers, and as well as in the case of chemotherapeutic agents. It reduced the toxicity of the chemotherapeutic agents by itself acting as an adjuvant in effective cancer therapy. Another, this one I'm just showing, it is 10:30 here. I'm just moving fast with these slides because this is a similar to the kind of study to that of the sesamol. But here I have used a biologically synthesized nanoparticle complex with gallic acid. So gallate, it is a trihydroxybenzoic acid. It is present in most of the berries and grapes, and even tea, green tea. And this has been used as a natural reducing agent for the synthesis of drug nanoparticle complex using silver nitrate. So it is found. This is just I am showing these slides because it will be useful for students who are doing their uh, in their MSc projects or anything. So they can prepare the nanoparticle complex of plant nutraceuticals or secondary metabolites for therapy or studying the anti-cancer activity or anything in their projects. So final year projects for MSc students. So I have used this biological green synthesis of silver nanoparticle drug complex of gallic acid. I named it as SNGA. So once the nanoparticles are formed, here I have used gallic acid and silver nitrate solution, 1% of silver nitrate solution and 1% of gallic acid, which was procured from Sigma, I think, gallic acid. And I have ultrasonicated it uh, in triple glass distilled water and sonicated it for 20 minutes and in dark for kept at 25 degrees centigrade. And when the nanoparticles are formed, it will give a golden brown solution, and it is called silver nanoparticle gallic acid complex. And I have done a just UV scanning, that is it shows like from in the range of 250 to 400. It's a formation of nanoparticles. And I have also done the XRD imaging of the nanoparticle formation, and it has showed good nanoparticle complex of the drug. And this is also I have done a CHEM electron scanning SM of this, and found that the nanoparticles were within the range of in the nanometer size, and it is done in the sophisticated stick QSAT Kerala. So it's the same kind of study. Here I have used 100 mg gallic acid and 100 mg equivalent of gallic acid nanoparticle complex, and it has also shown similar kind of results with like anti-inflammatory activity and protection against gamma radiation, membrane lipid peroxidation, and the it is also the antioxidant enzymes were restored in the normal tissue after irradiation, and GSH levels and bone marrow cellularity were restored, and the gastrointestinal damage is were corrected with the help of the drug complex, and the spleen colony formation, as I've shown. And there was like a 40% survival advantage in the lethal dose gamma irradiation in the animals. And the genotoxicity was DNA repair, and the micronuclear formation and chromosomal aberrations were reduced with the drug treatment. And there was a significant reduction in the tumor with the help of the nanoparticle complex of silver nanoparticle complex of gallic acid administration to the solid tumor bearing mice. And the same, like there was an apoptosis, induced apoptosis in tumor cells, and DNA damage, and it could protect the cardiotoxicity and the nephrotoxicity. And that's it. Actually, SNGA showed significant anti-inflammatory activity in both acute and chronic inflammatory models, inhibited radiation-induced peroxidation of membrane lipids, and maintain endogenous antioxidant status, and protect from radiation injury like genotoxicity, and synergetic action in the radiation-induced delaying tumor growth. And it can be used as an adjuvant in radiotherapy as well as in the chemotherapy. Thank you very much. And this is our campus, a portion of our campus. And this is the entire campus, Oklahoma University. And this is our medical center. I am working here, Department of Ophthalmology. This is our College of Medicine and Cancer Research Center. I was working here previously. Thank you very much.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah, thank you, thank you. You are welcome.
Uh, it was really interesting. The session is now open for discussion and questions. Participants, if you have any doubts, please feel free to ask.
Sir. Hello.
Yeah, yeah, please.
Am I audible?
Yeah, you are.
Sir, myself Jishnu Shankar, and
Mhm.
I have a doubt that, sir, actually, usually I have studied regarding this cancer moieties, chemical moieties. Wherever in those cases, all the assays, wherever in those cases, all the assays of this chemical moieties has been evaluated upon IC50 values or MIC50 values. But in the case of nanoparticles assisted moieties, does that not required for the evaluation?
It is needed actually. You can do uh, assays for IC50 values and the toxicity of the drug and this antioxidant status and all. We have used during my time. I have used that because you can even do some mutagenic assays, or you can also do uh, mm,
MTTS
the
is that?
MTT drug toxicity assays in the normal cells as well as and their effect in the cancer cells. So
Okay.
and I think the we have to check MTTSA and cell death, normal cell death in the case of inorganic nanoparticles which are chemically synthesized, and it will be much low in the case of biologically synthesized nanoparticles, the
Okay.
complexes. Yeah,
Okay. Thank you, sir.
you're welcome.
And sir, one more question rather than
Please.
this topic, not a, it's a general question.
Okay, please.
Sir, as you are working in the Oklahoma University, regarding
Mhm.
the entries to the abroad or to the abroad universities for the further studies, higher studies, what
Sure.
will be your suggestions? Could you please share the some
Actually,
suggestions?
yeah, it is possible that you have to clear the foreign language examinations like IELTS or TOEFL first of all, and you have to find a guide or a professor who is willing to give you the visa or take you as a student for your his PhD programs. It is always, I think, during the graduation program starts July or December time. You can see even in the university websites for recruitments for the graduate programs, and you have to find a professor, and you have to mail him personally and seek the position. You can do that. And
Okay.
I'm not
Yes.
sure about this like this time the pandemic, the COVID situation might have reduced the possibilities, but anyway it is possible. I wish you all the best.
Thank you, sir.
Okay, welcome. And I like to say that it is like 10:40 here and late night, and it is winter here. It is very cold outside, so I have to drive back to my apartment. I'm now in the lab to deliver this talk. So if we can stop it now, it will be very grateful.
Uh,
Yeah.
Dear participants, if you have any questions, you can either put a message in the chat box, and the feedback form has been circulated in the chat box. Kindly fill the feedback form. I
Sure.
hope that is there any further questions or discussions needed? Okay, I think the questions are over. Now I invite Dr. Chinta Thomas, the coordinator of the program, for the word of thanks.
Hello, am I audible?
Yeah, you are.
Okay, thank you. Good morning, all. Respected and distinguished speaker of the day, Dr. Gopinadhan Nair, respected principal, Dr. Biju Thomas, our beloved HOD, Dr. Suma Bino Thomas, IQSC coordinator, Dr. Manoj Narayanan KS, faculty members of the Department of Chemistry, and our most valued participants. It seems to be a great honor to propose the vote of thanks to all who have been part of this international webinar series. First of all, I would like to thank our speaker, Dr. Gopakumar Gopinadhan Nair, for being with us today and enlightening us with his knowledge. Today's webinar was very informative and it gave deep insights into the topic application of nanoparticles in cancer therapy and diagnosis, which is very relevant of the time. I'm pretty sure that the precious knowledge that Dr. Gopakumar Gopinathan Nair gave us would have inspired all of us to know more about this field and to perform research activities in related realms. Thank you, sir. Thank you for your
Well,
kindness to join us. With today's session, our international webinar series has come to a successful end. Before winding up, I would like to thank each and everyone who have been part of this international webinar series. This webinar series was conducted in 6 sessions with eminent speakers from all across the globe. During this webinar series, we got an opportunity to learn about emerging scientific work from various institutions from different parts of the world. Session 1 was handled by Dr. Jibin Abraham Kunos from the RNA Institute, University of Albany, New York. Session 2 by Dr. Oscar Castillo Garcia from the University of the Basque Country, Spain. Session 3 by Dr. Krishna Ramachandran from Shell Canada Limited, Canada. In session 4, we had Dr. Anuji Abraham from the Material Science and Engineering Wing, Bristol Myers Squibb, New Jersey, USA. Session 5 by Dr. Prashant Meneses from the Technical University, Berlin, Germany. And today for session 6, we have Dr. Gopakumar Gopinathan Nair from the University of Oklahoma Health Sciences Center, USA. I, on behalf of Basilius College, Kottayam, IQAC, and the Department of Chemistry, thank all the speakers for their generosity to accept our invitation and deliver wonderful presentations in novel arena of science. Once again, I thank all of them for being with us and illuminating us with their expertise. Now, I would like to thank our principal, Dr. Biju Thomas, and the management for giving us permission to organize this international webinar series. Our principal, Dr. Biju Thomas, has always been in support of such activities that would enrich the skill of the faculty and the students of the institute. I thank him for being such an impactful leader and motivating each of us. Words cannot begin to describe how thankful I am to a beloved HOD, Dr. Suma Bino Thomas, who has been the master brain behind this event. You have fostered a sense of support and appreciation that strengthen our capabilities. We are continually impressed with your ability to unite us. We feel very fortunate to have you as our HOD. Your guidance, encouragement, and moral support have made this event happen. Next, I would like to express my deep sense of gratitude to Dr. Manoj Narayanan KS, IQAC coordinator, for his support and advice for the well conduct of this event. It is my pleasure to thank the organizing committee who really worked hard to make this webinar series successful. I was fortunate to be backed by a very dedicated and motivated team, none other than my colleagues. I am greatly indebted to Dr. Jalaja J. Malayan, Professor Gino Matthew, Dr. Priya Thambi, Professor Sheetal Elizabeth Thomas, Dr. Anju Linda Varghese, Dr. Mitty Thambi, and Professor Christina Mariam Matthew for their wholehearted cooperation for the smooth conduct of this webinar series. This event would not have been successful without our teamwork. Thank you, dear teachers. Next, I would like to propose vote of thanks to our esteemed participants. We have around 300 registrations, including faculty members, scientists, research scholars, and students from various institutions. Without your support, this webinar would not have been fruitful. We appreciate your involvement and thank you for sparing your valuable time for the series. We believe that by participating in these sessions, you have gained useful knowledge and also new innovative ideas. Thank you very much for your active participation. Once again, I appreciate and thank all the speakers, participants, our college principal, IQAC Basilius College, management, head of the Department of Chemistry, the organizing committee, and all the individuals who contributed to the success of this international webinar series. Thank you all. I will end my speech here. Have a good day. Thank you.
With this, we have come to a conclusion of the end of the webinar, C International